How's everybody doing tonight?
We're good.
Good, good.
Excited.
Awesome, awesome. We'll see if we get a little bit of a better turnout here. We'll wait a couple minutes. I'm gonna try to start at 5 o'clock on the dot, but who knows? All right, so it's 5 o'clock. Welcome, guys. I'm happy to be here. I'm happy to see everybody here. I see some familiar names from last time. Uh, so I decided that we're actually going to change things up a bit for this week. If you have a question, don't be afraid to ask. You can interrupt me. We're also going to change it up. I might be a little more interactive with you. I might call out on some people, ask you guys some questions. Make sure you're grasping a lot of the things I'm going through. Right up front, this is going to be a little bit of a shorter presentation than last week. There's a lot. The concepts are a lot simpler, so there's not a huge amount of information. So maybe we'll be finished up by like 5:30 or somewhere around there. And then again, if you have questions, interrupt me. Uh, I might call out on you, ask you guys a couple questions, and we'll try to have a good time tonight. All right, sound good, everybody?
It's good.
All
Good.
right, all right. Let's get into it then. So today's lesson, guys. Today's aircraft systems, and we're going to talk about the way that aircraft basically function. We're going to talk about their systems, their components, their functions, and more. We're going to get into the engines, how they ignite themselves, the electrical systems, the way aircraft burn fuel, along with some other kind of risk factors like carburetor icing, using the right kind of fuel, and some of the limitations that you might uncover. Uh, and remember, guys, you got to look at aircraft systems from all angles. I mean, look at this guy right here. He's looking at, he's really getting it from the right angle. Uh, please don't walk on top of your Cessnas. It's not advised. All right, so we'll get right into it. Aircraft are powered by reciprocating engines, which are made of cylinders, pistons, connecting rods, and a crankshaft. And that's very similar to most engines in cars. Does anybody here know what kind of engine you'll typically find in a car? Is it a certain shape? Anybody want to step up and answer that? How about Andreas? You know what kind of engine you'll usually find in a car? What shape they are?
I have absolutely no idea. I'm not
Okay.
really a car person.
All right, that's no problem. Anybody here a car person? That what the most common shape of a car engine is? Anybody know?
Inline floor piston.
Oh yeah, inline's one. Inline is one, Danielle. Yep. And all right, I actually didn't see who that was. I thought it was Danielle. But yeah, you typically have inline, right? Or you have a V shape, right? You hear of a V6, V8. Well, airplanes are actually sort of in an H configuration. So the cylinders are directly opposing one another, and they call that horizontally opposed. And if you look here, this is a Continental engine, I believe. Actually, yeah, it's a Continental X370, and you can see here are the pistons, and you have two on each side. This is a four-cylinder engine, so you could say it's an H4, a horizontally opposed four-cylinder engine, and you see that they're opposite each other, and right down the middle of this engine, right, this is the basic of reciprocating engine. You have pistons which rotate a crankshaft. And what happens there is at the end of the crankshaft, you have a flywheel, but attached to this flywheel is the propeller. Now we could get into jet engines. Jet aircraft don't use this type of engine; they use a jet engine, right? So there's reciprocating, there's turbine/jet engines. But these are piston-powered reciprocating engines, and you have a propeller which is attached right here. And these engines actually operate on a four-step principle. It's called a four-stroke engine. And these strokes rotate the crankshaft, which rotate the propeller, which create thrust. Does everybody kind of get that?
Yep.
All right, awesome. So moving on, we're going to talk a little bit about those strokes, right? So there's those four strokes, and we'll start with the first one. The intake stroke pulls air and fuel into the cylinder. So you see here, it was just green, and it was pulling fuel in. And this is happening thousands of times every second. So there you go. There's the intake stroke. It's getting pulled in, and then it's getting compressed. So the second stroke is that compression stroke. And it compresses that fuel-air mixture that it just intook to make it more flammable. And what that does is that allows the spark plug here to ignite that mixture. So you see it gets compressed, and right there it got ignited. And when it gets ignited, it explodes, and it forces the cylinder back downwards. And that explosion, we call that the power stroke or the combustion stroke, and that forces that piston back down and continues to rotate that crankshaft. And the last and final stroke is when the cylinder returns back to the top, it pushes those gases out the exhaust valve. So you have gas and air coming in through the intake valve, being compressed and ignited, and then being pushed out the exhaust valves. Anybody have questions about that?
Just like a car.
Exactly. It's exactly like a car. It operates on the same principle. All right. And a little acronym we use. This is a good way to remember it. Suck, squeeze, bang, and blow, baby. That's the way you remember it, right? You got to suck in that air. You got to squeeze it, compress it. You're gonna hear a bang, and then it's gonna blow the rest out. That's a little humor in there for anybody that is into that kind of stuff. All right, so let's talk about a little bit how that air gas mixture is ignited, right? So reciprocating engines, we're not talking about diesel here. Diesel is a whole completely different story. But gasoline reciprocating engines require a spark. And most engines have a self-sustaining source of electricity called a magneto. And these devices use the mechanical energy of the engine, right? So they're connected to the engine. They're geared into the crankshaft of the engine, which is where the propeller is connected. So there's like that center kind of cylinder that's rotating inside the engine. And these magnetos are basically a magnet, um, similar to an alternator, but not quite. And they generate a spark. So it's a magnet and a coil of wires that generate a spark when turned. And this spark actually is what ignites the engine, so it keeps it running. Uh, but what we can say is that that magneto is not connected to any other part of the electrical system. So when we say it's self-sustaining, if you turn the master switch off in an airplane or turn everything off but have the magnetos on, the airplane doesn't need like power from a battery to keep the engine running, right? Because it's getting that energy from the engine. It's taking mechanical energy and turning it into electrical energy to spark the engine and keep itself running. Now, aircraft typically have two magnetos. You have a left and a right one for redundancy in case one fails. Now, if we look here at the diagram, you can see that the magnetos are connected to the engine via the crankshaft. And the magneto, the left one, is this little black box right here. And if you look coming out of it, you have wires. And these wires just go to the spark plugs, as you can see, right? And that's what keeps the engine running. And if we look at a little diagram here, you can see that here's your magneto switch that you find in the cockpit, and that tells you whether you want to use the right magneto, the left magneto, or both. And you're always going to leave it on both in flight. You have a right and a left just in case you need to test both of them, but you also have the starter connected to that. And I'll show you guys a little demo here. So I had a friend record this for us. So you'll see what's happening is he's going to turn all the power off except the magnetos. So there, ready? He's going to turn the master off, and you're going to notice everything's off, but the engine miraculously is still running. And that's because you have that separate ignition system, which isn't connected to the electrical system. But as soon as he turns those magnetos off, the engine will come to a stop, and you notice it's slowly losing power. And there you go. Does that make sense to everybody?
Yep.
I have a quick question.
Sure.
I this is the first time I heard about the magnetos, and now I understand it actually, and it's quite interesting. But I went through the checklist in MS 2020,
Okay.
and the checklist basically says, okay, turn on the engine with like both magnetos, and then go to only the right one, and you should see that the RPMs should go down a little bit, and then you do the left one, and it should also be lower, and then you put it back to both, and it should go up. And what I don't understand right now is why would it go up? I mean, if there's a spark, if there's the ignition, and you have the power, why would it go a little bit lower if you have only one of the
Sure.
magnetos turned on?
Yeah, so I can explain that. So there's more than one reason. You know how I said before, there's one reason we have a left and a right one for redundancy. That's not quite true. I was just trying to keep it simple. So you actually have two because it creates better power if you have two spark systems in the cylinder. So if you look at the cylinder of an airplane, and we'll go back to that, there's actually spark plugs on the bottom and the top. So the left and right magneto actually will power a cylinder twice. So you have two spark plugs per cylinder. You have two spark plugs per cylinder. One's powered by the left and one's powered by the right. So when you turn off one of those magnetos, you're not getting the same amount of spark as you were previously. Hence, you're developing less power because not all of the mixture is being burned as efficiently. Does that make sense?
That makes sense. Thank you.
Yeah, so when you turn that magneto to the left one or the right one, you're going to be developing less power for a short amount of time. And when you go back to both, you're going to be developing full power again. I hope that makes sense.
I got a question.
Sure.
If you operate with only one magneto, how does it affect the plane overall?
Uh,
The
you're gonna
RPM.
you're gonna see less performance and less power. So typically, you want to use both magnetos.
But if you operate with one, how much time can you fly?
You could fly indefinitely, but if you lose that magneto, you're going to, lose your engine. You will fly on one magneto. That's why you have a left and right one. But you always are supposed to have two in operation because you get the better power output, and that way, in case you lose one, you still have the other, and you can make an emergency landing as necessary. You're not really supposed to fly with just one magneto. It's a maintenance risk. It's a flight hazard because you're now at a higher risk of losing your engine, right? And you also won't develop the same amount of power, so you're not going to get the same performance, and you're not using the aircraft to the extent of its abilities. Does that make sense?
Yeah, thank you.
No problem. All right, let's move on. We're going to talk about electrical systems very briefly. All you need to know is aircraft typically have a 14 volt or a 28 volt electrical system, and they are supplemented with a battery, an alternator, or generator of the correct voltage. So if you have a 14 volt system, you're going to want a 14 volt battery and a 14 volt alternator. If you're a jet or a newer, GA plane with a 28 volt system, you're going to have a 28 volt battery and a 28 volt alternator or generator. And the reason why you don't see crazy voltages in airplanes, right? 14 volt is kind of close to the 12 volts that a car uses. And the reason for that is to reduce the risk of arcing and keep the risk of in-flight fire low. Does that make sense to everybody?
Yes, sir.
Now, you can get around this, right? Some aircraft, like the Piper Cub here, they don't actually even have an electrical system. So, and for P1, you could actually even use a Piper Cub for that check ride. You don't have to have an electrical system. But there are some limitations to that, like you don't have a transponder and things like that. But for all you need to know, some airplanes don't have an electrical system. All right, now we're going to talk about the way that airplanes actually get fuel to the engine, right? So aircraft, like cars, usually use one of two forms of fuel induction to power an engine. When I say fuel induction, I'm saying the way that the fuel transports from the tank and gets into the engine and then proceeds to be burned. Does anybody know how most cars are powered nowadays? How about let's call on somebody. Robin, you got any idea what kind of a fuel system a car has nowadays?
Aren't they pumps?
There is a pump involved, but I'm more referring to the
Yep.
way that it gets to the engine. If somebody knows, go ahead and shout it out.
Fuel injection.
Yeah, there you go,
Direct
Joseph.
injection.
Yep, exactly. Direct injection, fuel injection. That's the way that most cars today, modern cars, are given fuel. But airplanes, even new ones, a lot of them are coming out with carburetors still because that's just technology that airplanes have always had and they've proven to be reliable. So carburetors work by mixing air and fuel in an unpressurized chamber to create a combustible mixture. And we'll explain both of them in a little bit. We're going to go into the next slide. But fuel-injected airplanes are quite different. They actually mix the air and fuel directly before combustion, sometimes even in the cylinder. And that is where we get the term injection from. The fuel's injected. So we'll go to the next slide here, and we're going to talk about carburetors. So this is a little GIF I found of a carburetor, and you can see coming from the left here, you have air coming in. And as that air comes in, you get a low pressure area. So going back to last week, we talked about Bernoulli's principle, right? As a fluid speeds up, its pressure decreases. Does everybody remember that? If you were here last week or watched P1, do you guys remember that principle?
Yep.
Right. So what happens here is the carburetor actually gets thinner, and this is what we call a venturi. So when the air comes in, it has to speed up because the volume is restricted, hence the pressure drops. And what happens when that pressure drops is fuel will actually get sucked into the air because this fuel is you're essentially creating a vacuum in the fuel line, and to equalize that vacuum, this fuel gets sucked up into the air. And what happens after that is that fuel air mixture is now combustible, and that proceeds to the engine. Now you might be asking, well, how does that regulate engine power then? Well, if you think of it, as soon as you open the throttle, right? This is the float valve, and that's connected to the throttle, right? And this is the throttle valve. And what happens is when you push the throttle forward, this valve opens, which allows more air in and increases the speed of the air, which sucks more fuel, which allows more fuel to go to the engine and be burned. And that will create more power to the engine. Does that make sense?
Yeah, I got a question. So the throttle controls the air and the mixture controls the fuel ratio that goes
Okay.
into the carburetor?
That's no. So let me be a little more clear about this. So I'm talking just about the throttle right now. We're gonna talk about the mixture in a little bit, but the mixture is used to control the fuel air ratio. The throttle simply allowing more air in to the engine, and when you do that with a carburetor, you're automatically allowing more fuel to mix with the air. All the mixture does is control the ratio of fuel to the air because as you get higher up, the air density decreases. Um, so with the throttle, right, if you're allowing more air in, obviously you're going to suck more fuel into the air. But as you get higher up, that air that's being sucked in is less dense. So you have to decrease the ratio of fuel, and you do that with the mixture control. Does that make sense?
Yeah, I got it.
Right. So because of the decreased air density, you need less fuel, and that's what you use the mixture for. But the carburetor can't do that on its own, so that's why you adjust the mixture. The carburetor is allowing unadjusted will operate the same way, but you have the mixture to compensate for decreased air density. The carburetor doesn't care about air density, it's just allowing air to either go through or not go through. All right, let's move on. Fuel injection. So, like a car, this is actually a GIF of a car's cylinder. In a fuel injected engine, the air is actually mixed right before or inside the cylinder. On this GIF, you'll see it's mixed outside. High pressure fuel is mixed with air during the intake stroke of the engine. So you see here you have air coming in through the intake manifold, and here you have a fuel nozzle. And this high pressure fuel is aerated when it's compressed, hence high pressure, and it's injected. And you see the intake stroke, this intake valve will open, and that high pressure fuel and air will get sucked into the cylinder, get compressed, and ignite. You'll see here it ignites right there, and then it gets pushed out the engine. So those are the four strokes. But if this was a carburetor, you wouldn't have this fuel injected nozzle here. It would be coming straight from the carburetor pre-mixed. Does that kind of make sense?
Yes, sir. The
All right,
four
awesome.
stroke.
Exactly. All right. So we talked about carburetors before, but now we're going to talk about some of the downsides of a carburetor. Okay. So this here on the right is a carburetor, right? And you have air that comes in, gets shrunken down, decreases its pressure here at the venturi, and then flows out after it picks up fuel, and that goes to the engine, right? Now, sometimes, or actually most of the time, when air expands after it's mixed with fuel and after proceeding through the venturi, it actually cools down a significant amount. It drops its temperature. And that causes a lot of problems because if you have moist air coming into the carburetor and then mixing with fuel, that moisture, when it's cooled, forms ice. Now, does anybody here have an idea of why ice might be a problem in the carburetor? Does anybody want to take a guess at that?
You,
Engine roughness.
I'm sorry.
Mm,
What was that, Emerson? Sorry, I think multiple people were talking.
Engine roughness.
Okay, that's one thing. But what would happen if our carburetor completely iced over based off what we've learned so far?
No air.
Yeah.
That as well, but right, we're getting no air, and we're also, because we're getting no air, we're getting no fuel to the engine. So essentially, we're cutting the fuel off to the engine if the carburetor ices.
You flow the fuel.
Exactly,
Oh,
exactly.
yeah.
So you're basically going to starve the engine of fuel. It's gonna shut off if you ice off that carburetor. You're getting no air and no fuel to the engine. Now, how can we counteract that? Well, has anybody noticed in some of your planes, like in MSFS, have you noticed the 152 has this thing called carb heat?
Yep.
So the
Yes.
purpose of carb heat, right? Carb heat, you're actually taking heated air, right? So what happens is air flows into the engine, and there's a separate air duct for the carb heat. The air comes in actually through the bottom of the cowling and actually will flow over the exhaust manifold. And that exhaust manifold's really hot because you have hot gases that were just burnt by the engine. And the air will flow over the outside of that exhaust manifold, get nice and warm, and will actually go into the carburetor and melt that ice. Now, when you pull the carb heat on, you might notice that the engine actually performs worse because you have hot air going into the carburetor and it's less dense. So what happens is you actually enrich the fuel air mixture and the engine doesn't perform as well. But what happens when you get that hot air in the carburetor is it also melts that ice. So when you apply carb heat or carburetor heat, you'll notice that maybe your RPM tends to drop and the engine performance becomes worse. That's because the high temperature air becomes causes a less dense mixture and you're enriching the fuel air mixture. But you'll notice progressively over time as that ice melts, the engine performance will get better and it'll get better and it'll smoothen out and the engine won't be so rough. And because of that, you could say you've cleared all the ice out of the carburetor. Does that make sense to everybody?
So how do you know when to use the carb heat?
So the method for carbureted aircraft is anytime you notice engine roughness, you should just go ahead and put the carb heat on. But you're at a higher risk if you know you're in moist air. Let's say you fly through a cloud, or it's very cold outside. That's another risk factor. Um, anytime you notice engine roughness in those conditions, you should put carb heat on.
Okay, thank you.
would you leave the carb heat on as long as you're in these conditions, or is it more like you turn it on and then after 5 minutes, or when the engine is running smoothly, you turn it off again, and then after 5 minutes, turn it on again for a minute? Or
Sure. So have you noticed? Let's say the 152, right? You guys know what a tachometer is? A tachometer is the gauge that shows you the RPM of the engine, right? If you look at that tachometer, there's a green arc. And that green arc is mostly in carbureted airplanes, you'll see it. That green arc is when you should not have the carburetor heat on. If you're outside of that green arc at any point, you should put the carburetor heat on because that's when you're at the highest risk of getting carburetor icing. Because the engine isn't as hot. So anytime you're outside of that green arc on the tachometer, put the carb heat on. But like you said, going back, if you notice carburetor icing, put it on. Wait until the roughness goes away, and then turn it off. I wouldn't keep it on because you're not getting as much efficiency out of the engine. But if you notice engine roughness again, put it back on. Sound good, Andreas? I know that could be a little confusing if you're still
no,
confused.
loud and clear. Thanks.
Okay, sure.
James, I have a question.
Sure
Does
thing,
the
Daniel.
outside temperature have any impact on whether you're likely to get icing or not, or does this happen in all temperatures?
It does happen as high as I believe it happens as high as 40 degrees Celsius outside air temperature, but you are at a higher risk when you're colder. But that risk at 40 degrees Celsius is usually when you're going through a cloud. You're more likely to experience it. It is less likely, but it is possible. But yes, you are at a higher risk at colder outside air temperatures, usually below 0°C.
Okay, thanks.
All right, let's talk about aviation gas. So I know it's the octane ratings are different in Europe as in the US, but somebody here from Europe. So Daniel, you are obviously from somewhere in Europe. What kind of octane is usually the petrol over there?
For
I'm going to
cars?
say 75.
That's for a car, Daniel.
I believe so. I could be completely wrong. I think that's what it says on the fuel pump.
Okay. And
Yeah.
Catalan, did you? I heard you say
Yeah,
something.
I think it like here it's about 95 to 99, something like that.
That is very high. Okay. Anybody here from America that knows the answer? What's kind of our most common gasoline here in the States?
87 through 95, I think it is.
Yeah. So usually it's between 87 and 93, right? 87 is that regular unleaded fuel. Unleaded meaning it has no lead in it, the literal metal lead. And 87 is kind of what most cars take nowadays. If you have a higher end car like a Mercedes, you might put 91 or 93 octane in it. And just a quick explanation of what octane is. Octane is essentially the combustibility of a fuel, or how much compression it'll take before it explodes. So not everything needs a high octane fuel, but airplanes do need a high octane fuel. They're very high compression engines. So the main fuel that you'll find in airplanes is called 100 LL, and that stands for 100 octane low lead. And the low lead is because it's a leaded fuel. They actually put the metal lead into the fuel, and what that does is it raises the octane. So if you take that lead out of the fuel, it would probably be like a 97 octane. But if you add that lead in, it bumps it up to 100. And that 100 octane is necessary to prevent the fuel from exploding before it's ignited, right? If you were to compress fuel super hard, eventually it would explode. And that's the principle that diesel engines actually operate on, but we're not going to go too far into that. And importantly, fuels are dyed colors to represent their grade. And 100 low lead, which is the most common aviation fuel, is actually dyed blue. And this is it in this little jar here. It's dyed nice and blue, and you can tell that it's clear. There's no water in it. If there was water in it, you'd notice it right around the bottom here. And it's nice and clean. There's no dirt, nothing like that in it. So this is good fuel. And one other thing I didn't mention is fuel is used as an agent for combustion, but it's actually also used to cool the engine. It will actually cool the cylinders down because it's very cold before it's ignited. So this is a little bit of a long slide, but I'll try to be quick with it.
One quick question concerning fuel.
Sure.
What is the freezing temperature of 100 LL?
I'm not too sure on the specifics. It's below 0 degrees Fahrenheit. I know that. So below like negative 15 C. It's a very cold temperature. Most places it won't freeze.
Okay, so generally nothing to worry about also in a
Yeah.
airplane.
I'm gonna actually look that up right now for you. It's about apparently negative 58 degrees Celsius is its freezing point.
Okay, nothing to worry about. Thanks.
Yep. All right. So to continue.
Maybe in Serbia.
Yeah. Right. Exactly. Okay. So getting back to fuel. So we talked about the importance of using 100 low lead, that blue fuel. Now, let's say we put 87 octane, right? Regular gasoline from the gas station, and you put that in a plane. You're at risk of this thing that's called detonation. And detonation is the uncontrolled spontaneous explosion of the fuel and air before it's supposed to happen. So instead of happening on that power stroke like we talked about before, it might happen halfway through the compression stroke, and that becomes an issue because you're not developing the right amount of power and you're screwing up the way the engine rotates. Now, this detonation, you're having that fuel explode at the wrong time. It's actually causing an excessive amount of heat to be generated. Now, does anybody have an idea of why that might be a problem?
I think it could cause engine failure.
Maybe not quite that serious, but of course that's always a risk 'cause that could cause that. But really, you're overheating the engine, and you can wear out seals, you can wear out metal components, pistons, piston rings. You can damage the cylinder walls of the engine. Earl, I saw you were going to say something. Did you want to say something?
No, I was just gonna say pistons.
Okay, yeah, exactly. And that becomes an issue. So it's very important that you use the correct grade of fuel to avoid detonation. Now, there's also one other thing that fuel can cause. Um, this process is called pre-ignition, and pre-ignition is what happens when you don't have enough fuel in the engine, right? If you operate that engine too lean, as in you have not enough fuel for the amount of air you're taking in, it causes the engine to become very hot. Now, let's relate to cars for a second here. Cars and fuel will actually build up carbon over time, right? Because fuels aren't perfectly clean and when you burn them, they're actually a little bit dirty. So you'll get carbon in the cylinders of cars. And that's why sometimes you'll run like engine treatments to kind of clear out the gunk out of the engine. Well, the same thing can happen in an airplane. If you have gunk in the engine and you operate the engine too hot, those deposits in the engine will actually heat up so much that they will then ignite fuel before it's supposed to ignite. Hence the term pre-ignition. It's igniting before it's supposed to happen. And again, that's due to either hot lead spots, hot carbon spots in the cylinder, and those are typically caused by a lean fuel to air ratio or a lack of fuel in relation to air. Does that make sense? If anybody is confused about that, go ahead and let me know. Otherwise, we'll move on.
I got a question.
Sure.
Uh, so detonation and pre-ignition do the same to the engine, the same consequence?
Yes, they can have the same effects. Again, you're operating too hot. They're both creating excessive heat, right? So that again can damage pistons, cylinder walls, piston rings. And you also lose power. So you're not developing the maximum amount of power that you want to be developing. And you typically get both of these things when you're climbing out. And if you're not developing the most amount of power that you can during a climb out, you're not going to have the most efficient climb. And that creates a whole other amount of problems. Like you might not be able to clear an obstacle or get off a runway in a certain amount of time. So you want to make sure that you're using the correct fuel and that you lean your mixture properly for the type of flying being done. If you're at high altitude, you're going to want a lean mixture. If you're down at sea level, you're going to want a rich mixture or a mixture that has a lot of fuel in it. Does that make sense?
Yes. So
Yep.
how do I use the mixture?
Okay, sure. So when you go high up in altitude, right? As you go higher in the atmosphere, air becomes less dense. So because of that, you have to adjust the amount of fuel that the engine is burning. And the way you adjust the fuel to air ratio is by using that mixture control. So think about this, right? Let's say you have air, right? And it gets less dense. So compared to the air at sea level, if you go high up, the air is less dense. So if there's less air, you think it would make sense to reason that you'd also need less fuel?
Yes,
Right.
I
So
believe.
if you left that fuel ratio unchanged as you gained altitude, the air is becoming less dense as you gain altitude. If you were to leave the fuel, the ratio of fuel to air exactly the same, the fuel would become, or that fuel to air mixture would become more and more fuel and less air. So you have to adjust the fuel or decrease the fuel with the air as you increase altitude.
So in a practical example, I can notice that with the RPMs in my tachometer.
Yeah, so if you keep going up and you have the incorrect fuel to air ratio, you'll actually have a decrease in power. So I'll talk briefly about this. The proper way to lean in a 172 is to continuously and slowly reduce the mixture. And as you do that, you'll see that your RPMs will actually increase. But at a certain point, and we call this the peak, we call this peak RPM, you'll notice the RPM will stop and actually begin to decrease as you pull out the mixture. So what you want to do is you want to decrease the mixture or increase it enough to where you have that peak RPM. Does that kind of make sense?
Beautiful, thank you.
Yep.
No problem. All right, fuel systems, right? So we've been talking about fuel this whole time. Let's talk about fuel systems. Most aircraft will have two fuel pumps, right? One is engine driven, and the other is an auxiliary electric pump in case of failure of the engine driven pump, as well as aiding with startup, right? So think about a 172 R or an S model, right? The ones that are in MSFS and X-Plane. Those planes have an engine-driven fuel pump because they're fuel injected, and fuel injection actually needs a pump to create high pressure. But they also have an electric pump, and you'll notice that that's right by the lights. It's all the way to the left of your light control, and that's the high pressure pump that you use to prime the engine on startup. Now, if you look at like a Piper, they have an engine-driven pump both because they might be fuel injected, but because they're a low-wing aircraft and you need a pump to suck fuel out of the wings into the engine. On older 172s, they actually don't have an engine-driven fuel pump, and they actually get fuel to the engines by using gravity. The wings and the fuel tanks are above the engine, so the fuel will just naturally kind of fall into the engine.
So if you do aerobatics and like fly upside down with a top top winged aircraft
Uh-huh.
that doesn't have fuel pumps, the engine will stop at some point.
Well, not necessarily. If you maintain, we talked about G's last week, and G's are the relation of, or the load factor in relation to Earth's gravity. If you maintain 1 G throughout the maneuver, you'll actually be perfectly fine in a gravity-fed airplane because you have 1 G acting downwards on the aircraft at all times. So gravity is no longer towards the Earth. You're creating kind of, you could say, artificial gravity. Not really. I'm just using layman's terms at this point. But you're creating a gravitational force or a load that's towards the bottom of the aircraft, and that fuel will actually just continue to flow towards the engine. So if you're in a high-wing aircraft, you will not stall the engine depending on the maneuver you're doing.
All right, thanks.
But if you flew upside down and held it, like let's say you were just flying inverted, you would lose the engine because fuel can no longer at that point get to the engine. Does that make sense?
Yeah, thank you.
Okay, cool.
Certainly.
All right, and we'll show that electric fuel pump for you guys here. So you'll see he just turned the electric fuel pump on, and that's the clicking. He's going to hit the starter, and the engine starts. And at this point, the engine-driven pump will take over, and you'll see him turn off the electric fuel pump. But if you were to lose the engine in air, the first thing you should do is turn on this electric fuel pump as a backup. You might have lost the engine-driven fuel pump, and you now have a backup that you can use in case the engine one fails. All right, guys, spoiler alert. So, sorry, we needed to relieve some of this tension in here. So, spoiler alert, we're going to talk about oil next. Sorry, I heard somebody with a question. You can go ahead and ask that now.
I was just thinking about fuel systems, and I noticed with I don't know if like real planes have this, but like with RC, they backfeed air pressure from the muffler into the fuel system into the fuel tank to create pressure to force the fuel into the system. Does real aircrafts perform that way, or
Okay.
not at all?
So there are examples, and I'm only going into this because you asked, that they won't use exhaust because you wouldn't want to really pump airplane exhaust. It's all dirty back into the fuel tank. But there are some airplanes, like I'll give an example I know that has one, a Piper Comanche, that will actually take air. There's an air inlet, and will actually pressurize the fuel tank and assist it in getting to the engine. But it
Okay.
still has an engine-driven pump. It's just there as like an assist, like, hey, I'm going to nudge you towards the engine.
Gotcha. Okay, thank you.
No problem. All right, back to engine oil. So, oil, like a car, every engine, reciprocating engine has oil, right? Your car has oil. You check the oil. Oil changes, oil filters. Most reciprocating engines, or I should say all, will have engine oil. Now, engine oil is critical to the smooth operation of an engine, right? Because you have metal touching metal. If you didn't lubricate that, you're going to have a problem. And oil prevents direct metal-to-metal contact in moving parts. It's kind of like the I'm forgetting the cartilage in your bones, right? It acts between a buffer. It acts as a buffer between two hard objects. Now, an important thing to remember is if the oil level in an airplane falls too low, the engine temperatures may become excessive and you could possibly cause damage. And the reason for this is if you have a lack of oil, you have less of a buffer, and metal on metal parts create friction, and that in turn creates heat. So if you don't have the proper amount of oil in an airplane, you're going to have a lot of heat being generated. Um, and again, that excessive heat can also cause detonation or pre-ignition. There's a few possibilities that cause that. So one possibility is you have too much power being used. You have the incorrect fuel grade, like we talked about before. You have too lean of a mixture. You don't have enough fuel for the amount of air in the engine. Or you're operating with insufficient oil. You don't have enough oil. And these are all situations where you can be creating that excessive heat and you get pre-ignition and detonation. Now, to correct this, as a temporary solution in a climb, if you're experiencing that, lower the nose, because when you lower the nose, you'll naturally increase airspeed because you're not forcing the airplane up into the sky as much. And that increase in airspeed will increase the amount of air going over the engine, and that'll cool the engine and hopefully counteract the excessive heat. Anybody have questions about that?
If your oil level is low, I mean, I only saw that, for example, with a car, and if you drive up a hill, the level of your fuel tank is a bit lower than when you're like driving along a level road or down a hill, because the sensor, where the sensor is located, has that effect. Would it also make sense that, for example, if you have like lower oil level, that if you don't climb as quickly, more oil can get to the engine?
Um, Brian, you might have to step in on this one. So, airplanes, or a lot of airplanes, will have a wet sump system, which means that there's basically an oil pan at the bottom of the engine, and it's filled with oil. And as the engine turns on, it starts to splatter oil everywhere, and it kind of goes to wherever it needs to go to lubricate the engine. So if you're in a climb, it really doesn't, as far as I'm aware, doesn't affect the operating temperature of the engine. It has more to do with the level. Um,
I'm
but
sorry, I missed
well,
part of the question. I could step in, but I missed part of the
yeah.
question.
So
Can you say it one more time?
so he's asking if you're in a climb and you're low on oil. In a car, he was saying sometimes oil can access the engine easier, but depending on if you're a hill or not. My kind of thought was it has more to do with the level, and that I was explaining how there's a sump at the bottom of the engine. He's just asking if you're in a climb or a descent, if that will change the way oil is circulating in the engine, I guess.
And no, as long as you stay within the normal, like the category that the airpline's certified for, it's like a normal category. So, obviously limits like angle, bank, and pitch and stuff like that, not to go into that aerobatic category. Most piston driven engines, like a 172 or a Cherokee engine, for example, it's splashing that oil around, but it's also collecting at that sump at the bottom and going back through the oil pump and recirculating through the motor. So, as long as you stay within what the airplane's certified for, the engine will always be lubricated with oil. Obviously, how much oil is in the engine, that's the biggest consideration as well. That's why we always have like a minimum amount. Like a 172 can hold 8 quarts maximum, if I recall correctly, but 6 quarts is what most places say is the minimum. But it's just so you can circulate all that oil through. If you start running low on oil now and you start going to that pitch or descent, stuff like that, that's where you start running into some of those issues. That's one of those reasons we have a minimum. But it's all circulated through and lubricated no matter if you're on a pitch or descent. That's my understanding. Anyone wants to chime in?
I think you got it pretty clearly, Brian.
All right, thank you.
All right, let's keep moving. Let's keep the train boogieing. So now we're going to talk about propellers, and this might be a little bit complicated, but I'll try my best. Again, Brian, feel free to step in if you feel like I'm missing anything. So a 172, that is what we call a fixed pitch propeller aircraft, which means that the propeller cannot be moved in flight. The blades are kind of fixed. It's one big piece of metal, and it's set by the mechanic or based off whatever kind of propeller you have on there. And because of that, we can say that when you move the throttle, you're actually controlling the power output of the airplane. Now, some airplane, airplanes, and you might notice in X-Plane or MSFS, have a blue knob, and we call that the propeller control lever. And these aircraft, we say they have what's called a constant speed propeller. So when they say constant speed, they're referring to the ability of the propeller to maintain a certain RPM. So when you move that blue knob in the cockpit, what you're doing is you're actually setting an RPM on the tachometer. And you'll notice if you move that, if you were to move that all the way down while you had the throttle up, you could kind of position it at any RPM you wanted. Now, if you were to go flying and you set that RPM and adjusted the power, what you're actually doing is the blades of the propeller actually rotate. And if you look here at this little GIF, you see that the blade angle here is actually changing. And the reason the RPM stays the same when you set it with that blue knob is because the blade angle is changing and it's doing its best job to maintain that RPM. And that's why they call it a constant speed. It's trying its best to maintain that constant speed. Then the aircraft will automatically do that. It'll automatically change the blade angle once you set the RPM. And the way it does that is by regulating oil pressure. So you see here, the blade is actually being shifted by oil. You see oil here filling it up, and it's actually pushing on the propeller blade and forcing it to change its angle. And in an airplane that has a constant speed propeller like this, power is adjusted with the throttle, but the blue lever controls the RPM. Does that kind of make sense to everybody? I know this is a little bit confusing, and Brian might have to step in again. But if you have any questions, please ask.
So the blue knob controls like the angle of the blade,
No.
kind of.
So the blue knob does not control the blade angle. That's done automatically by the airplane. The blue knob controls the RPM, right? So you're actually setting the RPM you would like the propeller to maintain, which is the rotations per minute. Now, when you're going fast or going slow, or if you have wind constantly shifting, the propeller RPM is naturally going to want to change. So the way the propeller maintains this RPM is by changing the blade angle and finding the most efficient blade angle to maintain that RPM that you have selected. So you do not control the blade angle with the blue knob, you control the RPM, and the plane automatically changes the blade angle as necessary to maintain that RPM. Now, talking about that, this kind of propeller is actually a little more efficient. You'll notice in like a 172, right? If you were to go to cruise power and as you accelerate, you'll notice that the RPM will actually increase of the engine without you touching the throttle. As you gain airspeed, the wind is now starting to force the propeller to rotate faster. And as a result of this, you might have to reduce the power. What's great about a constant speed airplane is you can keep the same amount of power in, and the plane will automatically adjust the blade angle to hold the same RPM. And that way you can keep the same amount of power and have a more efficient cruise that way. Unlike the 172, where you might have to pull back the power to stay underneath the red line.
So my question here is, I guess, why would I need to adjust the RPM? Why would I ever need to play with the blue knob?
Sure. To get a better fuel burn, to get a more efficient cruise. Certain RPMs, according to the Pilot Operating Handbook, have better performance than others. And
Right. Okay.
when you have a prop that's full forward, right? If you have a prop that's all the way to the top, you're actually taking the smallest bite of air. The blade angle is its lowest, which means that you're taking basically a lot of big bites of air. When you reduce the RPM, the propeller now has to take bigger bites of air at a slower rate. So when you change the angle of attack by changing the blade angle, it may be more efficient for certain altitudes to use certain blade angles or RPM settings. Does that kind of make sense?
Yeah, and then that would be specified in the
In the manual.
operating
Yep, in
handbook,
the
right?
operating
Yeah.
manual. Yep.
Okay.
So,
And does it affect airspeed in any way? I suppose it does, but
yeah, I would say it affects cruise speed as much as the POH says it will, right? The pilot's operating handbook will give you the cruise speed that you should be attaining for a certain power setting.
Okay.
But it depends for every airplane.
Okay. Thanks.
May I?
Yeah, go ahead, Brian.
So like the one big benefit of a constant speed propeller in relating it to like a fixed pitch propeller, like what you would see on your 172 versus your Cherokee, a lot of times these flight schools or some airplanes have what's called a climb prop or a cruise prop, and that's as it relates to a fixed pitch, right? And so it's either you want to go fast as you get up in the air, but your takeoff runs may be a little bit longer because of the angle that it's fixed at, or so it's like a climb prop helps you get up faster, and a cruise prop helps you get faster. But what's nice about the constant speed propellers, you get all those benefits of those different types of fixed pitch propellers that you can adjust. So like you get all that performance that you need on takeoff to go down the runway and take as much air as it can. But as you get up in the air and you reduce the RPM back, you're reducing the drag and you can go faster. So you're getting peak performance out of the propeller at every stage in the flight as you need it. And that's one of the big benefits of the constant speed propeller, instead of having something that's fixed in place that you can't change. Does that make sense?
Yep.
Awesome.
All right. So I think Brian covered that pretty good. A lot better than I was explaining it. But we'll move on here. So now we're going to talk about left turning tendencies. So, have any of you taken off and noticed that your airplane likes to rotate to the left on takeoff?
Always.
Yeah.
Yep.
So, have you maybe thought, well, oh, there's got to be a reason it's doing this? And I know a lot of people, I've seen a lot of Facebook groups for MSFS and otherwise Discord. Why is my plane turning to the left? Well, there's a couple of phenomenon that explain it. And a lot of airplanes have these things called left turning tendencies. So airplanes that have a clockwise rotating propeller, and when I say clockwise, let's say you're sitting in the cockpit and the propeller is rotating clockwise. That's what I mean when I say a clockwise rotating propeller. They have a tendency to rotate or yaw to the left, and there are 4 main reasons for this. Probably the biggest one is torque, right? And that goes back to Newton's third law. You have a propeller that's rotating to the right or clockwise. So Newton's third law says for every action, there's an equal and opposite reaction. So that opposite left turning force or counterclockwise force is torque, and we could also call it the reactive force, and that forces the plane to the left. Another tendency is this tendency called spiraling slipstream. So as that clockwise rotating propeller creates thrust, it actually sends air spiraling around the airplane. And what happens is it goes underneath the airplane, comes back up around the left side, and hits the rudder, pushes the rudder to the right, and forces the nose to the left. So that's another tendency or another factor that causes the plane to turn left. The third force is called P factor, and I'll explain that with the diagram in a second. But with that rotating, clockwise rotating propeller, when an airplane is climbing and you have one blade going down and one blade going up, the blade that's going down is actually generating more lift. Because when it goes down and you're in a climb, it's got a greater angle of attack in relation to the air than the blade going up does. And that creates more lift or more force on the right side of the propeller, which pulls the right side of the airplane forward and to the left. And we'll show that with the diagram in a second. It might make a little more sense. But the fourth and final left turn tendency is called gyroscopic precession. And this acts similarly to P factor, but it's not due to lift or thrust. It's more to do with that the descending blade has more force, and this pulls the right blade forward. And I'll show you with the diagram here now. These are the 4 tendencies. So this is the reactive force, right? You have torque of the propeller rotating the plane counterclockwise as the propeller is rotating clockwise. You have that spiraling slipstream in which the air is spiraling around the airplane. It's hitting the rudder, pushing it this way, pushing the nose to the left. You have P factor, which this is what I said. You have the blade that's descending or going down, creating more lift, which pulls this side of the propeller forward, which causes the tail to come right and the nose to come left. And you have gyroscopic precession, which causes a yaw motion to the left because as the propeller rotates, there's more weight and there's a force that acts 90 degrees to anything that rotates, and that causes you to rotate to the left. Does that kind of make sense to everybody? These are the 4 forces which cause you to rotate to the left.
Very interesting. I didn't know that.
Yeah, it's a very interesting concept, and this explains, all the questions that I get asked. Oh, why does the plane turn to the left? These are the 4 main reasons. And it's worth it to say that not every airplane will have these tendencies. A Boeing 737 won't have this tendency because you have 2 engines for one, so you don't have torque. You don't have spiraling slipstream because it's not spiraling around everything, and you don't have P factor because you don't have a propeller. All right. So now we're going to talk about a little bit what you should know before you go flying. So prior to every flight, you should do at least a walk-around inspection of the aircraft. Make sure everything's in a flying order. Secondly, all pilots should know about how to operate their airplane. And we like to say this thing called RTFM, or read the freaking manual. And we say consult the pilot's operating handbook. The pilot's operating handbook, every airplane has one. Basically, we'll go section by section on how to operate the airplane. And thirdly, the use of a written checklist for pre-flight and starting the engine is recommended because this ensures that all the necessary items are checked in a logical sequence and make sure that your engine is good to go for a flight and that both the airplane is good to go for the flight. All right, now we're going to talk about something that you're actually going to need to know for the P1 check ride. For P1, you should know certain airspeeds for your airplane, and every airplane's different, so again, make sure you read the manual. The proper airspeeds for climb out, for landing, and for stalls. So I wrote down the basic ones that you should know for P1, but always feel free to go into detail and find more. So VA is the maneuvering speed. So let's say you're doing steep turns for the P1 check ride. VA, the maneuvering speed, is the airspeed you should be at for those maneuvers. If you're doing steep turns, I believe that's the only real maneuver you're going to have to do for the P1 check ride. So you should do steep turns at that speed. VX is the best angle of climb speed. So let's say you're taking off from an airport and there's like a 50-foot tree at the end of the runway. Well, you're like, how am I going to get over that thing? So in that case, you'd use this speed called VX, and that's in the operating handbook, and that's the best angle of climb speed. And what that means is if you rotate off the ground, you're going to create the biggest angle in relation to the ground, and it's going to get you the greatest amount of altitude in the shortest amount of distance. So I don't know if I can draw on this PowerPoint. I don't believe I will. But we'll draw it at the end. But yeah, you're going to imagine you have like a really big, like 45-degree angle. It's going to get you the most angle out of your climb in relation to the ground. VY is the best rate of climb speed. Now, let's say you want to get the most altitude in the shortest amount of time. If you're just doing a normal takeoff, you should really climb out at VY. And this will give you, the most amount of altitude in 2 minutes, or 3 minutes, or 5 minutes, or 10 minutes. And typically that's the speed you will climb out with after you've cleared an obstacle. Now, VSO is the stall speed in a specified configuration, or dirty, or you could say landing configuration. So this is the speed at which the plane's going to stall with the flaps out, with the gear out. And if you look at the airspeed indicator here, this goes at where all the speeds are actually marked on the airspeed indicator. So VSO is actually marked here at the bottom of the white arc. VS is if the airplane was clean, if you had the flaps up and the gear up. This is where the plane would stall with the flaps up and the gear up. That's the bottom of the green arc. VNE, or the never exceed speed, this is the speed which you should never go past in an airplane because you're risking structural damage. That's the red line here on the airspeed indicator. VNO, or the normal operating speed, that's the fastest you should go. You can go above this speed if you're in smooth air. If you're in turbulent air, you should stay in the green arc and not proceed past VNO. VFE is the maximum flaps extended speed, which is represented by the white arc. And just so you guys know, this is actually the airspeed indicator out of a Cessna 152. So if you're going to use the 152 for your check ride, you have VFE, flaps extended. You can put the flaps out at 85 knots. You're going to stall right around 47 knots clean and about 43 knots dirty. Does that make sense to everybody? You guys understand why we have these speeds?
Yeah, I got a question. Where is
Sure.
VA?
Where is VA? So VA is actually not marked on most airspeed indicators. You'll actually find that in the POH, and I'll explain why. The reason you don't mark VA on the airspeed indicator is because as your weight changes, the maneuvering speed actually changes, and you'll see that in the POH. Most POHs will give you the maneuvering speed at max weight, and they'll say, hey, for every 10 knots that you lose, or every 100 pounds you lose, the airspeed will decrease by 5 knots. That's why you don't mark it on the airspeed indicator, because that speed is actually changing based off how heavy you are.
Thank you.
So what happens if you put flaps down above VFE?
You risk doing damage to the flaps. Now, I will say this. VFE is the speed at which the airplane was certified to not be damaged if you were to put 100% of the flaps out instantly. You could do that below VFE. Now, some airplanes, like the 172, there's a placard that actually says you can put 10 degrees or 1 notch of flaps out below 110 knots, but you can't do any more than that. You have to get below VFE before you can put the rest out. So VFE basically says, hey, you can dump all the flaps at this airspeed and not risk doing any damage to the airplane. So typically you want to wait to put the flaps out until you're in VFE. But some airplanes, again, you can put some flaps out above that. All right. So that pretty much concludes our presentation today. If you have any questions, we can go over them now. Thanks for coming. Hope to see you next week. I can't quite remember what the topic is next week, but I'm sure it's interesting. And if you have questions, ask away.
So,
Go ahead.
so what's the risks of going over or below the maneuvering speed?
So I'll give you the official definition of VA. VA is actually classified as the airspeed at which you can do one full control deflection, a single control deflection. So you could pull all the way back on the elevators, you could push all the way forward on the elevators, you could roll all the way left or all the way right. Just one of those. You could do one of those at VA and guarantee that you won't damage the airplane. That's the official definition. That's why it's important, because as you change weight, you're going to change the limits of the aircraft. So it's important to do. Yeah, so VA, my friends are filling me in. You'll also stall before damage will occur to the airplane. So that's why it's critically important to do your maneuvers at that airspeed, because you will stall before damage occurs, and you'll also stay within the envelope of the aircraft for what it's certified. Does that make sense?
Yeah.
Why does the gauge only start at 40 knots?
I'm not exactly too sure. Brian, do you want to go into this? I believe it's because you need a certain amount of air moving into the tube before it will.
Yeah. It's just a factor of the pitot tube being able to actually sense air as airspeed with that forward momentum. So every airplane's like, and some of your newer airplanes sometimes can get a little bit better with that. But most airplanes start in the 30 to 40 knot range simply because they just need that forward momentum and ram air going through the pitot tube to be able to read it. That's the main reason.
All right, thanks.
James, I have a comment.
Sure.
It's regarding the propeller and the constant, I guess, the constant speed
Sure.
propeller. And just a comment that I had noticed in checklists for either cruise speed or descending or climbing with those type of aircraft that have that type of propeller, that it actually puts in there sometimes. And I'm glad you had that explanation because I always was wondering about this. But they will actually say, your throttle is at this, whatever. I have a question about the throttle part of it. Propeller at 2,500 RPMs or 22 RPMs or depending if you're, either cruise or whatever. The throttle, it was mentioning all the time, like it would put a number down like 25.
Yes.
And going like I don't know, millimeters or 25
Yes.
inches
So
or whatever.
yeah.
There's
So
another, I know there's
it's actually
another
inches. Yeah. So
gauge that you can control that as far as the throttle is concerned.
yeah. So they're two separate gauges, right? You have the RPM gauge or the tachometer, and what you're referring to is the manifold pressure gauge.
Yeah, that's it. Yeah.
And the manifold pressure is measured in inches of mercury, and that's actually just the pressure at the inlet of the throttle body of the engine. And that's basically measuring how much power you're forcing through the engine, but it's not the RPM of the engine. That's just how much power you're developing.
Right.
Right? And the blue knob simply just controls the RPM. Now, a combination of those two will produce optimal thrust, but it's just giving you the option to manually control power and manually control RPM, unlike a fixed pitch propeller, which they're combined into one.
Okay. Yeah, I just thought because someone made a question about that RPM part of it. And I remember flying this when I know it was a Beechcraft or which one it was, that I'm decreasing the thrust, but the RPMs were staying the same.
Right.
And then it hit me that there's a difference there. But again, I was going through the checklist and say, hey, this is what you're supposed to do on a descending. You
Right.
set all these parameters on there, so it's like an extra step from the 172 or any other.
Right,
Plane
for
I
cruising and stuff like that. I got you.
Right, that you got to think about. Okay, thank you.
No problem. Anybody else? This is your time to shine if you got a question.
Yeah, I got a question, but about the electrical system
Okay.
of an airplane.
Mm-hmm.
If I lose all my fuel and I have an engine failure, but I still have electricity, and what time?
You mean like well, that depends for each airplane, right? So let's say you run out of fuel, right? In a 172, you will. So the airplane's no longer generating power to the battery or electrical system because the alternator is now useless, right? The alternator is an engine-driven generator that keeps the main electrical system charged. So if you lose that engine, you're no longer spinning the alternator, which is no longer generating electricity. So you'll have power to for a certain amount of time, until the battery dies out. So you won't instantly lose power. You still have a battery, and that battery is rated for a certain amount of time, depending on the airplane. So does that kind of make sense?
Yeah, where can I find that information?
I'm not. I believe it should be in the POH. Brian, do you happen to know?
Hold on, I'm sorry. I missed. What was the question one more time? I'm sorry.
He's trying to find how. Oh, Mateo, you got it.
Go for
Yes,
it.
it is on the operating systems pages of the POHs usually. In the electric system, it will usually be under a note specifically, at least on the 172 POH.
Okay, thank you guys.
And one thing that I figure we should go over, as Mateo mentioned this to me, if you lose an engine, right? You mentioned losing an engine. All aircraft have a best glide speed, right? So if we go back to last week for you, those of you that were here, remember we talked about there's that point where drag and lift become equal, right? So there's that point where you have the least amount of drag but the most amount of lift. And we remember that drag curve where if you're at a certain airspeed, you have the least amount of drag. I think Catalin, you were here last week. Do you remember that graph?
Yep.
Okay,
Yep.
so if we look at that graph, that part of the drag curve had an airspeed associated with it. And why that's important is if we lose our engine, well, we don't want to have a lot of drag, but we do want a lot of lift. So That airspeed at which we have the least amount of drag and the most amount of lift is called the best glide speed. And we have that speed in case of an engine failure because we want to get the most range or the most gliding distance. And that's represented as VG. And you can find that in the POH. Depending on the aircraft, it might have a gear up best glide, a gear down best glide. I figured I should cover that quickly. Just remember that some aircraft have, or all aircraft have a best glide speed, and it's in the POH. And that's there in case you lose your engine. All right. If nobody has any other questions, I guess we can finish up. Oh, wow. We burned through an hour. I didn't even think it was that long.
Hey, I did have a question about the magnetos again.
Sure.
So, like in the pre-check, you know, I know you're supposed to test left and right, and I know we talked about that before. But should you see the RPMs increase or decrease?
Decrease.
Decrease. So if they do if they don't decrease, right? What should you do to remediate that?
Well, if they don't, well, here's what'll happen. If it doesn't decrease, it means that maybe your magneto is just really good performing. Because if it were broken and you went to it, the engine would just stop.
Okay.
So it should decrease, but it doesn't necessarily mean it will.
So by the checklist, really, if you went from both magnetos to left, for instance, and if the engine stalled, right? If the engine stopped, then that would mean your magneto. You got to take it back. You can't.
Exactly. Yeah, you can't fly. Your that would mean you. So you selected that you want to use the left magneto. If the engine dies, that means you got a bad left magneto. You got to go either get it fixed or get a new one.
Okay. Cool.
Doesn't the checklist for the RPM, it's a no more drop than this rather than it has to be a certain amount?
Exactly. Yeah. So it shouldn't drop more than a certain amount. It doesn't say that it can't not drop. It just can't drop more than, let's say, I think the 172 is 125 RPM or something like that. Actually, I have a 172 checklist in front of me. Let's look. Let's see, where is it?
Momentarily, I will add, if the RPM doesn't drop, it means that magneto might have a fault where it will still keep firing as well.
Yep.
Right.
Agreed.
That could also be it. Yeah. So the 172R at least is 150 RPM. It can't drop more than 150 RPM.
So basically, as the wear of a magneto increases, so does the RPM that it drops to when you put it on that particular magneto, right?
I'm not 100% sure what you're asking. Can you just
so if I have a brand spanking new magneto, if I switch just to that one, it's gonna drop by a certain amount. But if that magneto is actually older, it's gonna drop more.
No, not necessarily. Not necessarily. You're just checking to make sure that it's in a flight-worthy condition and where it's producing enough spark. Where if you lost the other one, you would still be able to run the engine.
So, and ideally, should they drop the same amount of RPM, or
right?
It doesn't matter?
So that's another thing we could talk about. In the checklist, it'll also say that the difference in the amount they drop are limited. So the 172R, let's say the left magneto drops 110 RPM and the right magneto drops 120. So they're only 10 RPM apart, which is fine. But let's say so there's a limitation between the amount that they can drop, and that's 50 on the 172R. So let's say the left drops 110, or let's say the left drops 90 and the right drops 150, which is the max. Well, they're 60 RPM apart, so that's no good. You got to take the plane back and get it fixed.
Right. Okay. Gotcha. Thanks.
Aren't the magnetos connected to the spark plugs, or no?
Yep. Exactly. Yep, they are.
So it could be a faulty spark plug as well, not the actual magneto itself.
You gotta remember, there's 4 spark plugs attached to each magneto.
Yeah,
so it could be. You could be right. And a way you can test that is you can actually lean the mixture a lot, because sometimes those spark plugs get like gunked up and fouled, and if you lean the mixture, it'll actually burn a lot of that stuff off. But that's one way to try to alleviate that. That's not always the case. But that's one thing that you can do to try to remedy that.
Sure.
Is there a specific RPM you need to reach before testing the magnetos?
Yep, and that'll be in the POH. The 172R is 1800 RPM.
18. Okay, thank you.
Each aircraft's different. My Arrow's 2000 RPM.
Yeah,
so
that's very engine and propeller dependent.
All right. Any other questions, or I think we were okay. All right.
Thank you so much.
No problem, guys. I hope
Thank you.
see everybody next week, and thanks, guys, for coming.
Thank you.
Have a good one, guys.
Thanks a lot. Appreciate it.
Thank you, guys. Thank you, James.